Assalamu alaikum, everyone. Let's continue our discussion on chapter 12. We have been discussing about the psychrometric chart. So we'll discuss few more properties that we see in this chart and talk about how we can make use of them. So the first thing that I want to talk about is the mixture enthalpy per unit mass of dry air, which is also mentioned in the figure A9, which is the psychrometric chart. Now, this is going to give you the enthalpy for the entire mixture, not just for air or the water vapor in it, right? It's going to give you this term that we're looking at. And it's going to give you the enthalpy of the mixture per unit mass of dry air. Now, one key change between the enthalpy values that you would calculate here or the values that you would get from table A22 is the fact that just for the purpose of figure A9, right, just for the psychrometric chart, the enthalpy for dry air is calculated as CP times temperature, where temperature is in degrees Celsius. Okay, the CP is also fixed, of course. We're going to assume a value of 1.005. Now, this is perfectly fine because for all our applications, we typically are not interested in the absolute value of enthalpy. You're not looking at what is the value of H1 or what is the value of H2. What we're looking for actually is H2 minus H1, for example. So it doesn't really matter whether you take the enthalpy, whether you take the temperature in Celsius or degrees Kelvin, as long as you're looking for a difference, right? So if you're going to make use of this chart for determining the enthalpy for the mixture, make use of the chart for both states. Do not get H1 from figure A9 and S2 by using, the table A22. This will create a problem. Get both enthalpies either from figure A9 or from the figure A22, table A22 and the other table that you need for the water rate. So that's the key point to remember. Now, when we're looking at this particular state, right, the state that's indicated in blue, if you want to find out its enthalpy, well, we need to look up the constant enthalpy lines. All right, so this blue line right here is the scale for mixture enthalpy. It's going to have different values for different enthalpy, and this part right, these lines right here, which are shown with the blue dot moving around, these lines that I'm showing again in red, these are the different constant enthalpy lines. So if you want to find out the mixture enthalpy for this moisture state, you just have to draw a line parallel to any of these constant enthalpy lines that meets this axis. Okay, so you draw this line here, and the point where it meets is basically the value for the mixture enthalpy at that state. All right, so this is how you would determine the mixture enthalpy for this particular state. Any other state, you do the exact same procedure. Now let's look at these other properties that we can determine here. Wet bulb temperature. All right, we already spoke about wet bulb temperature, and we said that we can also measure it using a thermometer with its bulb covered with a wet wick or a wet cotton cloth, for example. Now, if you want to make use of the psychrometric chart to determine the wet bulb temperature, well, it's all plotted along the saturation line, which is refers to a relative humidity of 100%. So this is basically the scale shown in blue that has the wet bulb temperature for different states. All right, so the lines of constant wet bulb temperature are sort of parallel to the lines of constant enthalpy. Okay, so these are the lines that I'm showing here that represents lines of constant wet bulb temperature. All right, so you can see it's also written in right here. So again, if you want to find out the wet bulb temperature corresponding to this particular state, draw a line parallel to these lines, right? And the point where it meets, that's the wet bulb temperature that you're looking at. Again, if you're looking at a state where the relative humidity is 100% to start off with, well, at this condition, the dry bulb temperature is actually going to be equal to the wet bulb temperature. So this is basically the only place where these two are equal. Otherwise, in general, when phi is less than 100%, the dry bulb temperature would be greater than the wet bulb temperature. Okay, and this is what we see in most cases. All right, so now let's talk about the volume that we can detect or that we can measure from the psychrometric chart. The volume that we get here is basically the volume per unit mass of dry air. Okay, so it's not just the volume, it's sort of the specific volume if you want to think about it. But here it's it's normalized with respect to the mass of dry air and not the mass of vapor, simply because the mass of dry air remains constant. Now, we have several lines of constant volume, just like we had lines of constant enthalpy and so on. And this line right here is basically one of the lines for constant volume. Now, when we talk about volume, what we're saying is essentially that the volume that we get here is going to be either the volume of dry air or the volume of water vapor, okay, per unit mass of dry air, of course, in keeping with the fact that the Dalton model requires that each component fills the entire volume. So what exactly are we talking about? Go back to the Dalton's law of additive pressures, right? So we know that the pressure of a mixture is going to be equal to the pressures of individual components, so pressure of air plus pressure of water vapor, provided this pressure of air is measured while air is kept at mixture temperature and it fills mixture volume. All right. So same way, PV should be at mixture temperature and mixture volume. So basically the volume that we're going to get from here is basically the volume of dry air per unit mass of dry air or volume of water vapor per unit mass of dry air for the conditions defined by the state. Okay, so just in really simple terms, do not assume that this is the volume that we get here is the volume for the for air plus water vapor. This is not the case. Okay, so it's either air or the water vapor. All right, so the quantity, the volume per unit mass of air, it's actually written on the line itself, right? So if you have the line of constant volume, you'll see some number written on top of it that indicates the volume that you're looking for. Again, we have a couple of examples that we will solve, and we'll show you how exactly we can make use of this. Okay. Now let's start with a couple of examples. Here we have been provided the temperature, the dry bulb temperature that is, as 35 degrees Celsius and 40% relative humidity. When nothing is mentioned, whether the temperature is dry, whether the temperature is wet bulb, dew point, or dry bulb, by definition we assume assume this to be the dry bulb temperature. All right, because dry bulb temperature is basically the ordinary temperature that you measure using a thermocouple or a thermometer. So these are the two things that are given. We have two properties, and we know from the state postulate that if you have any two properties, we can completely define the state of a system and then get everything else from there. So now we're going to make use of these two properties and then determine the rest of the things that we need here, which are humidity ratio, mixture enthalpy, wet bulb temperature, dew point temperature, and also the volume per unit mass of dry air. Okay. Now I have color coded them to indicate the lines that I'm going to use to pick up these values from this chart that's given here. Okay, so let's start with the humidity ratio. And before we start with any of this, actually first let's go ahead and identify where the point is. Okay, so we're looking at a dry bulb temperature of 35 degrees Celsius. The x-axis is the dry bulb temperature. Okay, so we look, this is 30 degrees Celsius, this is 40. We're looking somewhere in between. So this is the point that we're looking for, 35 degrees Celsius. Let's draw a vertical line through it. Okay, so this line represents all the states that lie on 35 degrees Celsius dry bulb temperature. Now we're looking at something which also has a 40% relative humidity. So we're looking at lines of constant relative humidity. Which are these lines, right? So this is 90%, 80%. We go on till we find this line right here, which is 40% relative humidity. So let's go and see where it meets. Okay, so this is the point where the dry bulb temperature of 35 degrees Celsius meets with 40% relative humidity. So this is the point that we're looking for. Okay,